let's go for inductance, capacitance, resistance also we did. We calculated resistance also, I remember, right? Then let me give inductance, capacitance, and all these things. Then you can start solving the problems, right? Yeah. The formula for inductance. Inductance formula is LA. If you take one conductor, its inductance formula is C. L internal plus L external. Okay. L internal is equal to mu naught mu r by 8 pi Henry per meter. Internal inductance is independent of area of cross section, radius, diameter, and all these things. It is independent. Internal inductance of a conductor is independent of any physical parameters, right? Where mu naught is 4 pi into mu naught is 4 pi into 10 to the power minus 7 Henry per meter. Mu r is equal to 1 for overhead transmission line. Relative permeability, overhead transmission line made up of aluminum. Yes, aluminum. Yes, it is for aluminum, right? Next, L external is yes mu naught mu r by 2 pi into natural logarithm of distance between the conductors. This is the configuration of the conductors. This is the configuration of the conductors. Center to center distance is D. This is RA. This radius is RB. Right? D by RA Henry per meter. You see, per meter inductance it is. If you want total inductance, multiply with the number of meters. Suppose the fellow in the examination gives a question in terms of kilometer, the distance in terms of kilometer. For every 1 kilometer, we know that 1000 will be the number of meters. Right? Now, LA total will be mu naught mu r by 8 pi plus mu naught mu r by 2 pi into natural logarithm of distance by RA. This way you will get total Henry per meter. See, I can derive all these things, but our motto or aim is not for the derivation. Our main aim is for examination. In what way it is meaningful? It is meaningful for us to remember. That way we will remember. Right? There is a pattern for it. Right? The only see the difference between L internal and L external you can find. If you observe the L internal formula, it is independent of physical parameters like area of cross section, diameter, these kind of things. But it is going to depend upon number of kilometers. As number of kilometers increases, obviously L internal will increase. If length of the transmission line doubles, inductance also doubles. Right? Now, if I further simplify this, I'm going to get like this. LA is equal to, right, 2 into 10 to the power minus 7 into ln of distance by RA dash. In the last class, I clearly mentioned dash indicates 0.7788. The dash indicates what 0.7788. LA is equal to 2 into 10 to the power minus 7 into ln of d by 0.7788 times of RA. That d can be replaced with GMD. Yes. If you can find the GMD of this, GMD of A, yes. Could you please tell me GMD of conductor A? Conductor A, one conductor, 1/root of A to B, the distance is D. 1/root of D means D only. What is GMD of B? GMD of B is 1/root of D. That is also D. Right. So what is GMD of system? I am doing here. GMD of system is equal to 2 GMDs are there. That's why square root of GMD A into GMD B, that is equal to D. That is equal to what? D. So this is going to be GMR of conductor A. This is GMD A. Now that can be happily replaced with 2 into 10 to the power minus 7 into ln of natural logarithm of GMD of conductor A by GMR of conductor A Henry per meter. Henry per meter, right? Yes, that is about LA. Now, obviously, LB also same. Only the thing it is going to change 2 into 10 to the power minus 7 into ln of, yes, GMDB by, yes, GMRB, GMDB by GMRB, Henry per meter. Henry per meter. Am I clear? Yes, please. Am I clear? Come on, man. Which one you wanted me to repeat, ma? Shreya? Which one? Which part exactly? It's not possible to repeat the entire thing, na? Just you let me know what you wanted me to repeat. Yes, just two conductors are taken, inductance of each conductor. This system. Yeah. So D stands for GMD, right? We got it as GMD. GMD of A is D, right? 0.7 RA dash stands for 0.7788 RA, which is equal to GMR. We replace this one with GMD, this one with GMR. This is conductor A, this is conductor B, LA and LB. Sir, I want L circuit. What does it mean by L circuit? L circuit is equal to LA plus LB. If anyhow here GMDA is equal to GMDA is equal to GMDB is equal to GMD of the system. GMR of A is equal to GMR of B, that is equal to GMR of the system if you can take RA is equal to RB is equal to R if you can take. Now L circuit will be 2 times of LA, that is equal to 2 times of LB, since L circuit is equal to LA plus LB. LA plus LB. Now, if length of transmission line increases, then resistance increases, inductance increases, inductive reactance increases proportionally. Why proportionally? Henry per meter. If number of meters doubles, obviously inductance will double. Inductive reactance also will get double. Inductive reactance also will get double. Yes. Am I clear here? Am I clear here? All of you. Shreya? Yes. Now, what is the power taken by inductor, that is reactive power QL of transmission line, is equal to we have to write 3I square into XL. This capital L is of line inductance, not load inductance. Sir, what is the topic name? Transmission, man. We are continuing from GMR. See, come on, last class you did not remember, man. RLC constants. Resistance we did. R is equal to L by A. Input power, output power, power I given. Then loss we calculated. After that, a voltage is also given. Right? Then we found the resistance in the last class. Power system conductor. RLC parameters now. What is power system conductor? I told you that we are using ACSR conductor, aluminum conductor with steel, steel reinforced. We are using standard conductor to reduce the skin effect. Right? Number of strands also we discussed in the last class. That is a number of layers. First layer is 1, then 6, then 12. That way we discussed, right? So it is always very important to get to be in touch with the previous discussion. Then you can understand very easily. See, every transmission line is going to have RLC parameter. No, see, if you take a transmission line is a simply a conductor this way, simply a conductor, right? And this is phase A, this is phase B, right? And this is phase C. This is phase A, this is phase B, this is phase C. Every transmission line is going to have resistance, inductance, those are series elements, and shunt capacitance and shunt conductance also. But most of the times, let me write it as capital G, this is C, this is R, this is L. This is a leakage current. I leakage it is very, very, very small. So that is almost near to zero. Therefore, this will be neglected. So most of the cases, shunt conductance is there. Don't be under an impression that this G and this R are reciprocals. No, this resistance is wire resistance. This shunt conductance is the conductance that is because of insulators. Okay, overhead line insulators. Right. So this is going to draw reactive power QL. This is going to supply reactive power QC. So this is going to have some power loss. Yeah, resistor always create power loss. Now this is single phase equivalent circuit. For three phase, that's why these three become. Now this is 3 I square into XL. I told you in the last class that for transmission line current and phase current both are equal, exactly same, exactly same. Clear? And this current is called as charging current. Now, inductance is a series element. Whenever any series element is there, we have to write the formula I square into that value, resistance and reactance. Now, this capacitance is shunt value. So, the reactive power supplied by the shunt capacitance is equal to V square by XC, we have to put that. V square by XC, we have to put that. This should be line voltage, line to line voltage. Then this itself, what is line voltage? Root 3 times of phase voltage whole square divided by XC. So 3 into V phase square by XC. So 3 into V phase square into 1 by XC will be omega C per phase. Right? Now here also 3 into I square into omega L, that is 2 pi F L, 2 pi FL. Yes. So yeah. Neglected because of minimum voltage. No, why voltage is minimum? Not voltage is not minimum. This G itself is very small value. This is very small value. Small value, please. Not smally. Small value. Very small value. Since why? Since see, this is the tower, this is cross arm, this overhead line insulators. This is our transmission line. This will be in terms of mega ohms or giga ohms. Now, giga ohms. Now, this current leakage current which is flowing to the ground, this leakage current flows this way. As this resistance is in mega ohms or giga ohms, right? Then its conductance 1 by giga will be very small. As the conductance is small, leakage also will be small, right? Let me know whether you understood that or not. Okay, observe it. I'll wait for a minute. If you have any query, you can type it in the chat box. Yes, ma'am. Shall I go forward? Yes. So that's about inductance and resistance. Capacitance is C per phase. This is the formula. 2 pi epsilon naught epsilon r. Let me take two conductors, then I'll define. Means if I take two conductors, conductor A, conductor. So capacitance is always formed between two conducting bodies having potential separate based on the electric. This is capacitance AB. Now this is the capacitance to neutral. This is CAN. So this is the capacitance to neutral. This is CBN. So CAN is equal to 2 pi epsilon naught epsilon r by ln of D by RA. Do remember in the capacitance calculation, you won't get dash that 0.7788, you won't get. The reason being here is the electric charge, net electric charge inside of a conductor is zero. Net electric charge. Okay, the net electric charge inside of a conductor is zero. That's why you won't get RA dash, that is RA only. In inductance calculation, we will be getting RA dash. Right? CBN also same 2 pi epsilon naught epsilon r by ln of d by rb farad per meter. See, AB will be, it is not 2 pi, it is pi only. Pi epsilon naught epsilon r by ln of GMD by GMR, GMD of the system by GMR of the system farad per meter. So line to line capacitance is means between two conductors the capacitance is half. I can write between two conductors the capacitance is half of that of phase to neutral capacitance. Half of the of phase to neutral capacitance. Am I clear? Yes. Now try these questions, man. Yes. Answer this question. Simple question. You can try. Simple question. Do not look at the solution as I told you. I know that solution is visible there, but a solution that is given over there for the flexibility of the students who won't attend the class, who are going to listen this class in recorded form. And they will be referring to the document directly. Some people, for their flexibility, the solution is taken in type of. Yes, Master. Yeah. option D. Yes, very good. See, that is very simple now. Simplest question. 2 into 10 to the power of minus 7 into L is equal to ln of md by dm. You want this one to be minimum. So for that, GMD should be low, GMR should be high. Option is D, for Delhi. Right? This question directly you can answer. You need not to solve. All these are previously asked PSU examination questions. These are not my own questions. Yes, what is saying? The ratio of line to line capacitance and line to neutral capacitance. Line to line capacitance is half that of line to neutral capacitance. Answer should be 1 by 2, option A. Since this is a direct formula, this is not log, this is ln, this is ln. Try this question, please. Try with your calculator. In the examination, calculator is not allowed. The question will be given in such a way that calculation is going to be easy. Otherwise, the total form will be given, that ds is there, no? The total value will be given. See, it is not possible for us to calculate without calculator power 1 by 7, power 1 by 49, these kind of things. Okay, try this. Yes, try this please on your own. Yes, what is asking? A conductor is composed of 7 identical copper strands, each having radius r. Okay. 7 strands means 2 layer. Na? First layer is 1 strand, second layer is 6 strands. 1, 6, 12, like that. Okay. Then what is a self GMD? Self GMD stands for GMR only. To remember, self GMD and GMR both are same. Self GMD is for bundle conductor or for this strand conductor. So if single conductor is there, we will take GMR. We will take GMR, right? Yes, I'll wait for 1 more minute. Try this. Yeah, I'm waiting so that. Yes, option C, perfect. No, it is not option C. Let me see. Let me tell you. See, there is a 1 strand. Above that, 1 more layer. 1, 2, 3, 4, 5, 6. Now, this is first one. Its radius is R. Its radius is how much? Capital R taken. Let us also take capital R. Right? So, GMR of cap 1 is equal. Its own is R dash. This center to this center to R. This center to this center to R. This to this center to R. This to this into 2R. This to this into 2R. This to this into 2R. How many distances these are? 1, 2, 3, 4, 5, 6, 7. Seventh root of. Sorry. Seventh root of. GMR, every conductor its own distance R dash. From that conductor center to another conductor center, how many such combinations are there? All combinations you take, how many distances you have, that much root you have to take. So GMR is equal to seventh root means whole power 1 by 7 you will get whole power 1 by 7. R dash means 0.2 into 2. How many twos? 1, 2, 3, 4, 5, 6 means 2 power 6 into 0.7788 into R power 7. You calculate this, you will get. That is only you got 0.88. Why you get 0.88 whole power 7? No, that is not correct. That is not correct. This is answer. This is answer. Try this, you get. Okay. Next question, please. Try this. Yes, yes. Small new learning is there in this one. Try this, all of you. Yes, ma. What is saying? The internal inductance of a long cylindrical conductor of radius r carrying a sinusoidal current of I, RMS value is given as just what is that? Mu naught mu r by 8 pi into 10, 8 pi, that's all. Mu r is 1. Mu r is 1. Mu naught is what? Mu naught is 4 pi into 10 to the power of minus 7 by 8 pi means 4 pi by 8 pi will be 1 by 2. 0.5 into 10 to the power of minus 7 Henry per meter. Repeat. Yes, ma. Answer is option C. That question it is. Try this, please. Oh, this is not required. This will come later. Yeah, answer this, please. See, you know the formula, but only thing is that fellow given options in terms of log, but we learn in terms of ln. We learn in terms of ln, right? Just you have to know, you should know how to convert from ln to log. That's all. That will give you the answer. Lot of big solution is there. I will make it as very simple. You do not worry. Yes. Option B. I'll do this. I'll do this. Very simple. We know capacitance formula, but see, ln of T by R we have capital D we taken. Let V take the same. D by R is equal to, let's take as some x. Apply e power on both sides. So D by R is equal to e power x. Now log apply on both sides. Log d by r is equal to capital log x log to the base 10. Log means to the base 10 to is e. What is x? X is ln of d by r. So ln of d by r is equal to log d by r by log of e to the base 10. Calculate this and put there. That's all. In place of ln of d by r, put that log d by r by log e to the base 10. That's all. You'll be getting the answer, right? What is the answer? C12 is equal to pi epsilon naught epsilon r by log of capital D by small r into that will go upside log of e to the base 10. Log of e to the base 10 farad per meter. Farad per meter, right? Yes. So epsilon naught value, if you substitute, what is epsilon naught? 8.85 into 10 to the power of minus 12 farad per meter. So you can convert it to microfarads and all as per the units you can do that. Right? Answer this question, please. Try this. Yes, ma'am. What is saying? The inductance of a single phase two-wire power transmission line per kilometer get doubles. Means inside logarithm should increase by square for the inductance to become double. Means that d by r whole square if you get, that will get as 2 into 10 to the power of minus 7, right? Means both the distance should be double as well as both the distance is square, not double. If distance is 6, you must have 6 square. If r dash is some value, so you must have r dash square. Both should be squared, not double. Double is different, square is different. 4 double is 8, 4 square is 16. Okay. Wires is double. When the distance between the wires is doubled, is not possible. When the wires is increased by 4 times, distance between the wires is increased by 4 times. So 4 times means 4 into d. No d square. Wires increased as square of the original distance. So little bit option C is matching. Actually, to speak, R dash also should double. Yes. I repeat. Little bit it is not matching, not completely. Are you clear, man? Am I clear with the answer? Yes. Sir, for today I can leave because I'm not. Okay, man. Okay. Fine. You can leave. Right? Option is C. The reason is, actually, we speak, D should be squared, R dash should be squared, then you get it as ln of d by r dash whole square. Then 2 will come this side, 2 into 10 to the power of minus 7 into ln of d by r dash. Now this is going to double, means the ratio should be squared. But in the options that is not there. More or less option C is near. It's not exact to speak, it is near. Okay. Yeah. The next question is about surge impedance. Okay, let me give you some points related to surge impedance and we will solve the question. What is surge impedance? Let's see. Let's see surge impedance. Surge impedance. ZC or it is also called as characteristic impedance. It is also called as natural impedance. I repeat, it's called as characteristic impedance. It is called as natural impedance. It is the impedance offered by the equipment for sudden changes or surges. I repeat, it is the impedance offered by the equipment for sudden changes or surges. ZC is equal to every transmission line is going to have ABCD parameters as I discussed previously. Parameter B by C, or if you take the transmission line as distributed parameter null, right? Small z by small y, or what is small z? Series part R plus j omega L by G plus j omega C, R plus j omega L by G plus j omega C, right? And or it is under root of ZOC into ZSC. What is ZOC? Open circuit impedance. ZSC is short circuit impedance. Or under root of L by C. This is for a lossless transmission line. Lossless transmission line means resistance is equal to zero. I repeat, lossless transmission line means resistance is equal to zero. Shunt conductance is also zero. One important point is ZC is independent of length of the transmission line. ZC is independent of the length of the transmission line. Means what? A 1 kilometer transmission line is having 50 ohms of capacity impedance. Same transmission line, if you increase the length by 50 kilometers, 100 kilometers, 1000, 10,000, 1 lakh, how many number of kilometers are going to increase? That doesn't matter. That capacity impedance is going to remain same. Right? Next is surge impedance loading. SIL. Surge impedance loading. That is called as power. That is V square by ZC. V line to line. If you take this is 3 V's. If you take that as phase voltage, V phase square by ZC. This is single phase power value of surge impedance. Single phase power value of surge impedance loading. Right? Am I clear? Yes. Yes or no? V square by ZC. Now, there are a few conclusions here I'm giving. See, if loading on transmission line, loading means power, loading on a transmission line is less than surge impedance loading. That is, Z impedance, load impedance is greater than surge impedance. See, power is less. Loading means power. Power is less than this. Power is less means impedance is small. I repeat, power is less means impedance is small. Then the conclusions are, then the very first conclusion is mod VR is greater than mod VS. Receiving end voltage is going to be more than sending end voltage, which is called as current effect. I repeat, receiving end voltage is going to be more than sending end voltage. And this particular effect is called as what effect? Current effect. Yes. And receiving end current is less than sending end current. And receiving end power factor is less than sending end power factor. These are the conclusions, right? Next, this is the first case. Case 2 is if loading is exactly equal to surge impedance load, that is Z load is exactly equal to ZC, then mod VR is exactly equal to modulus. Mod IR is exactly equal to mod IS. Receiving end power factor cos of IR is exactly equal to cos IS. Receiving end power factor and sending end power factor are exactly same or equal. So third one is if loading is greater than surge impedance. Means what? ZL is less than ZC. Load is high. Impedance is this. Because our is V square by we have to put always by, because always we connect our loads in shunt, not in series. Right? Then receiving end voltage is less than sending end voltage. Receiving end current is going to be more than sending end current. And receiving end power factor is less than sending end power factor. These are the conclusions one should remember. Yes. So those are the very important conclusions. Yes, one should remember. Right? Yeah. Now there are few questions on this. Okay. Surge impedance and surge impedance modeling. We'll see that. This question design analysis part. Okay, that is Peterson coil and these kind of things we saw already, right? Yeah. Now the question is, for a transmission line, the open circuit and short circuit impedances are 20 ohm and 5 ohm respectively. Then the characteristic impedance is, just now I given you a formula. Need not to refer this solution. Don't refer this English solution. ZC is equal to under root of ZOC into ZSC. So that is equal to under root of 20 into 5. That is equal to root of 100. How much is making the simplest value? Simply that is 10 ohms. Characteristic impedance of a transmission line is how much? 10 ohms. Easiest question. Look at that. That is very easy. Right? Try. This question will come in the next class, that is in voltage control topic. You will be getting, if you remember this formula, that's voltage control is very easy. You will see that. Okay, I did not given you the formulas and concept of voltage control. Okay, now so velocity of wave propagation. Let's see that velocity of wave propagation. We'll see that. Then we go to the question. What is velocity of wave propagation? When we release a wave onto a transmission line, yes, we are releasing a wave. Voltage, current waves are released at the sending end side at a time t is equal to 0. Now, this is a receiving end side, right? When your time is exactly equal to capital T. Capital T is the time taken for the waves to move from one end to other end completely. Means voltage and current waves are present at t is equal to 0. They are at the sending end. When t is equal to capital T, those will reach to the receiving end. Again from receiving end to sending end. Now, the velocity of the traveling wave, which is traveling, is equal to, the formula is 1 by under root of LC. That is going to depend on the inductance and capacitance of the transmission line. Now, if you do that, you are going to get it as 1 by under root of mu naught into r, yes, epsilon naught into epsilon r. If you substitute the values of mu naught and epsilon naught, you will be getting it as 3 into 10 to the power of 8 by under root of mu r into epsilon r meters per second. Sir, I wanted it in kilometers. That will be 3 into 10 to the power of 5 by under root of mu r into epsilon r kilometers per second. Next is wavelength, lambda. Wavelength wavelength. What is wavelength? Wavelength means it is the physical length of the transmission line that is required to complete one full wave. Yes, one full wave means how many degrees? 360 degrees. How many radians? 2 pi radians. It is the physical length of the transmission line required for completing one full wave. Lambda formula is 2 pi by beta wavelength. Sir, what is beta? Beta is equal to omega into under root of LC. See, if you take gamma, which is called as propagation constant. Sir, you are introducing a lot of new things. What is that? Propagation constant says how your wave is propagating from sending it towards receiving it or receiving it to sending it. Means I'm speaking something over here in that. Suppose assume this one as an offline class. You are sitting in this class. There are some 400 people sitting in this class. When I'm speaking, my voice will travel to the last bench, but in decreased format. Means the magnitude of my voice keep decreasing as the distance from me is increasing. Right? I think I'm clear. In the same way, when we release a voltage or current on both waves at one end of the transmission line, those waves travel from this end to this end. When they are propagating from one end to another end, they will subjected to some changes. What are the changes? Magnitude of the wave may increase or decrease. So what is practical decrement in magnitude? And the phase angle of the waveform also will change. These two things will happen. That is given by this propagation constant gamma, which is equal to under root of small z into small y. What is small z, sir? R plus j omega L ohm per kilometer. What is small y, sir? G plus j omega c mho per kilometer. Mho per kilometer. Gamma units are per kilometer. And gamma, if you simplify, you will be getting one real part and some imaginary part. This is called as attenuation constant. This will decide whether the magnitude of the waveform is increasing or decreasing. If alpha is positive, the magnitude will keep increasing. If alpha is negative, magnitude of the waveform will be decreasing. But which is practical, sir? Magnitude will keep decreasing with respect to the length of transmission line. Right? Beta is called as quadrature component. Beta is called as quadrature component. So this will tell us the change in the phase angle. Okay, beta is equal to omega into LC. Just now we learned omega into 1 by root LC will be V, then root LC will be 1 by V. Right? So beta, omega is what? 2 pi f by velocity. Yes. Now, what is lambda? Lambda is equal to 2 pi by beta, 2 pi f by v, 2 pi gone, is equal to velocity by frequency, our childhood formula. Yes. Wavelength is equal to velocity divided by frequency. We learned this one in our childhood, right? Now let's go to the question which is asked on this question. Try this question, please. I am giving you 2 minutes of time. Yes, 2 minutes of time. Solve this. After that, I will solve. Yes, I'll solve this. What is saying? The inductance and capacitance per unit length of a lossless transmission line are 250 nanohenry per meter and 0.1 nanofarad per meter. That's fine. The velocity of the wave propagation and characteristic impedance of the transmission line are very simple. Velocity V is equal to 1 by under root of LC. The values of LNC you substitute here. And ZC is equal to under root of LC. Just this is meters per second. Yes, this is ohms. That's all. Ohms. That's all. See, substitute. That's all. ZC is equal to under root of L by C. Sir, what it is not mentioned is it has lossless transmission line, but the values of resistance and shunt connectance are not given. Therefore, by default, it is taken as lossless transmission, right? See, today we will stop here for this class, right? We'll stop here. And next class I'll be taking. We are going to complete this entire transmission part. What we are left with is voltage control and reflection, refraction parts of this wave traveling. Reflection and refraction parts of this wave traveling, right? And voltage control, little bit of cables and overhead line insulators. These four things are left. Questions on that will be solved. First we'll be learning concept, then we go to questions, right? Any questions are there, you can ask me. Yes. If you have any questions on the things that are discussed today, there are few questions in this. There are few questions on this, on the same topic, right? Those questions you can solve. Okay, those questions you can solve.